ability of this structural element to resist failure. So that is strength. Now, what is stiffness? It is the ability to resist deformation. So there may be some material which is deforming, which is have high deformation. It is elongated or compressed when a load or force is applied on the material, but it may not fail. All right. So what we will say, it is strong, but the stiffness is less. That way, right? These are not same meaning. So strength is directly related to failure and stiffness is related to deformation. So if we have some structural element, some material which is stiff, which is very stiff, that means the deformation or deflection is very less in that material. Okay. Then we have the definitions for homogeneous material and isotropic material. What is homogeneous material? A body is said to be homogeneous if it has identical properties at all points in identical directions. We have a body, we have a certain volume of some material. So in this material, what will happen? Identical properties at all points. Okay, all this point and this point. The properties in x direction here and this property in x, sorry, let's say this is y direction. In y direction here and properties in y direction in the other point as well is exactly similar. So that is a homogeneous material. So homogeneous material will be of the same type, it is of one property. Okay. Then there can be isotropic material. What is isotropic material? Isotropic material, if at any point it has identical properties in all directions. Okay. Now, isotropic is what? This is same type of volume we have of certain material, and at one point, what we are concerned with one point only. Here, the properties in y direction, properties in x direction, and properties in z direction, they are all same. So that is an isotropic material. So there will be another type of material, orthotropic. What will happen in orthotropic? Properties are identical in orthogonal directions in 90 degrees. You are writing something in okay. Okay. So okay, fine. Continue. So this is homogeneous, then isotropic. Then we have another type, orthotropic. What is orthotropic? Properties are similar in orthogonal direction. What is orthogonal direction? In 90 degrees. Okay. So when we discuss isotropic, we said x, y, z only, but actually it is going to be same this way, this way, this way, this way, every direction. It is going to be same. In orthotropic, what will happen? It is same here and it is same on the 90 degree orthogonal direction. It is going to be same. Okay, that way. Then there is two terms, one is toughness and one is resilience. Again, toughness is related to the fracture point. How much energy is accumulated in the material till fracture, okay, till failure. That is toughness. Okay. And what is resilience? Resilience is same kind of thing. It is the energy that is accumulated in the material, or it can take the impact, take the pressure, force, stress, etc. But up to elastic limit only. So resilience is up to elastic limit and toughness is up to fracture point. And this is the stress strain curve. We already know that. So toughness, if that by definition, what toughness is the ability of the material to absorb energy during plastic deformation up to fracture. And toughness is the ability of the material to withstand bending or application of shear stress without fracture. That is why we are talking about until fracture. Fracture is the last point. Until fracture, how much is the ability of that material to withstand bending or any other forces acting on it. Copper is extremely tough, but cast iron is not. So what happens? Copper, you know, goes a long way before it fails. So therefore, copper is extremely tough. There may be elongation, there may be deformation, doesn't matter, but it can. So you're okay. What is toughness? It is the ability of the material to absorb energy up to fracture. Okay, so that is toughness. And what it means, copper is extremely tough, but cast iron is not. That means copper, takes a lot of energy before it fails, but cast iron cannot. Okay, so see, the cast iron may be stiff. It may take less deformation. Okay, we applying some stresses, some forces. It is not deflected much, so that is stiffness. But it will fail after some time without much deflection. So it is stiff, no doubt. But copper, it say for example, it is deflecting. It is going more and more. Okay. So copper is deflecting more and more, say for example, but it is not failing. Okay, so that is what makes copper tough. So if we don't fail, then we are tough. That's it. Then toughness, the same thing. It is the capacity of material to absorb energy. Done. What is modulus of toughness? Energy absorbed per unit volume. Okay. The entire energy absorbed, that is the toughness. Now we are saying there is another term, modulus of toughness. What is that? The total energy absorbed divided by the volume of the material. So that is what? Energy absorbed per unit volume. So that is going to be modulus of toughness. And it is equal to what? It is equal to the area under the stress strain curve up to the fracture point. Then there is another term, resilience. It is exactly similar to the toughness term, but resilience is up to elastic limit. Okay. So in this stress strain curve, we are saying that this is almost up to this point. We have the elastic limit. Beyond this, it is not anymore elastic. So this is energy stored in the elastic region. Okay. Then there is another term, hardness. What is the difference between hardness and toughness? Hardness is the resistance to scratching, cutting, or abrasion. Okay, so one material is applying friction on another material, and the material is not producing any scratches. That means the material is hard. Okay. And toughness is the what? Resistance to friction. We already talked about that. The toughness is the energy absorbed till fracture, till failure. So toughness is related to ultimate failure. So again, same thing, hard materials are scratch proof this way. Hard materials affected by strength and plasticity of the material, and toughness, it will be affected by rate of loading, temperature, and knots effect. Okay, what is knots effect? Knots effect is this. Okay. Whenever, say, we are pulling some metal, what happens after some time? There will be some neck formation, knots formation like this. So that is knots effect. So it is related to failure. And these are the tests through which these are measured. You will find it in transportation lab. I think it was this time, if you have of I don't remember if it is this time or in the next semester. So transportation lab, we have this kind of test. So if it is possible to do offline, you will perform this test. Now, average shear stress is very easy. Total force by the area, corresponding area. Here we have the total force here, and this force is acting upon in this area. Okay, so this area, it is force is acting average stress. And one more thing I would like to add here, that when we were talking about stress and strain, okay, what happens? We have a material. We are applying stress. What is the stress? be it shear stress or direct stress, the formula is force by area. When it's direct stress, we are looking at here, right? The area which is perpendicular to the applied direction of load. That is the area we are looking at. That is the cross section we are looking at when it is direct stress. And when it is shear stress, we are looking at this area, right, which is parallel to the applied force. Now, in this case, when we are talking about a direct stress, what may happen after some time, what may happen, we are applying load, the force F is constant. Say, for example, after some time, what may happen, the material is elongated. There is some strain in the material. It is elongated. If it is elongated, so what will happen? This cross section will reduce. So say, for example, there is 100 kilonewton force. Initially, the cross-sectional area was 10 centimeters square, say, for example. After some time, what will happen if your force is still 100 kilonewton and your cross-sectional area now reduced to 8 centimeters square? So what happens? What happened here? This is our true stress. Okay, we don't take this stress, but this is our so what happens? 100 by 8. So that is our true stress actually, right? Like this is a true area corresponding to what this entire 100 kilonewton load is acting on. But so when we first discussed, we didn't mention about this. So the stress strain curve was like this, something like this. But if we consider the actual stress, right, because the area is also decreasing. In this way, what we were doing, we were considering the same initial cross-sectional area. Okay, and the material is kind of failing. But what happens if we consider the true stress? Then what will happen? Since this is decreasing, right? The denominator is decreasing, so the overall stress value may be increasing only after failure. So that is the difference between the true stress and the average stress initially that we were talking about. Then how this performance test is done, tension and compression tests are done. We have this kind of standard material which we use in our universal testing machine. So we have this standard material which has standard length, standard cross-sectional area, and this will be used in a universal testing machine. It will be put here. We will be stretching it. We will be applying force. Okay, the forces will be measured, and then we will be uh, performing these tests up to failure. Okay, and we will note down what load were applied, what is the elongation, what is the change in length. Based on that, say this is the elongation, L minus L naught. Say L naught is the original length and L is the final length after applying the load. That can be L minus L naught, that is elongation. Now what we can do, L minus L naught divided by the original length. So this is what change in length divided by original length. This will give us what is the increase in length, what is the percentage increase in length with respect to the original length. If we multiply it by 100, we shall get the percentage elongation. It may be some value like 20%, 15%, something like this. So this is percentage elongation, and this is a very important property of steel that we use in various construction activities. So this test machine will give us what is the yield value, what is the ultimate strength, what is the percentage elongation. Okay, you know that we have different types of steel, right? We have different type of steel, like we have Fe 250, right? We have Fe 415, we have Fe 500, we have Fe 500 SD, like that. So all those materials we can test here, we can find out what is the percentage elongation. Now if the percentage elongation is more, that means what? The material can increase in length without failing more. So percentage elongation is an important property for these reinforcing materials. If the percentage elongation is higher, that means it can extend, that means it can increase in length without failing, that means it is a ductile material. What is the definition of ductile material? A material that can be subjected to large strains before it ruptures, before it fails. Okay, so mild steel is the example of ductile material that we use in construction. So what it means, this is our initial, say for example, it can extend up to something like this before it fails. So that is a ductile material. If it cannot, it is brittle material, right? That we know already. So how we are comparing the material, how much ductile it is? We are conducting the tension test through the universal testing machine. We are finding out the percentage elongation, okay? And that will give us how much ductile. With that way, we will be able to compare one material with another material. So this is percentage elongation. What is LF? This is LF. This is the final length. This is L naught. That is the original length. L naught is the original length. So final minus original divided by original into 100 percentage. So that is giving us percentage elongation. And then we shall compare that this material has 15 percentage elongation, this material has 20 percentage elongation, another material has, say for example, 10 percentage elongation. So that will be, that way we will be able to compare that this material is the most ductile specimen among the three. So in certain construction where we need higher ductility, we will be going with this material that way. Then percentage reduction in area also can be done. It is defined in necking reason. What is necking reason? So I don't have a picture, I guess, for neck. Oh, yeah. No. See, what is necking reason? I think we discussed it. We have a material, we are applying force, right? Slowly it is increasing in length. It is increasing in length, and what will happen at one more point, somewhere it will start reducing in cross section. Okay, that is the necking reason. Okay, so there we are calculating the percentage reduction in area. N naught is the original area, AF is the final cross-sectional area. Again, N naught is the original cross-sectional area. So the change in cross-section divided by original cross-section multiplied by 100 will be giving us the percentage reduction in the cross-sectional area. Then another important thing is certain materials have definite yield point, while some other points may not have that definite yield point. Okay, so this is when materials do not show definite yield point. If there is a straight curve like this, okay, like this, we know that this is the yield point. Okay, this is where the material is starting to elongate quickly and it is yielding occurs, its resistance is decreasing suddenly, right? So that is the yield point. This is a definite yield point. But the diagram shown here, the figure shown here, what we see that this is how the stress strain is moving, right? So it is not having a definite yield point that we can take. So what we are doing, we are saying that we will take normally 0.2 percentage strain as a proof strain. This is 0.2 percentage strain, 0.2 percentage or 0.002. So at that value of strain, what we will do, we will draw a parallel line. Parallel to what? Parallel to the initial portion of this stress strain curve. Remember, this is a stress strain curve. Initial portion will be linear and elastic. When it is linear, it is a straight line. Then it will be changing, right? So it will be parallel to the initial portion of the stress strain line. We will draw one line, and this line cuts the stress strain diagram somewhere here, right? Now the stress corresponding to this point will be our yield stress. Okay, so this is offset method of determining yield strength when we do not have a definite yield point. And we know brittle material, it will fail, right? It will fail this way. It will not be elongated. Okay, just go through the definition. So brittle materials do not have well-defined tensile fracture stress since appearance of initial cracks is quite random. Okay, so its behavior will be random and it will fail suddenly. Then there is another important term. We will again see this term, but I just mentioned it here. Poisson's ratio. Okay, what is Poisson's ratio? It is the lateral strain by longitudinal strain. This was our material. No, the dotted one is our initial material. We applied some stress, some tensile stress. So what happened? The material deformed like this. The material deformed like this. So when the material will deform like this, obviously the cross-sectional area will reduce. Here the dimension will reduce. So that is what we are talking about. So there will be a strain in this direction, lateral direction, and there is a strain in the longitudinal direction. Now lateral strain divided by longitudinal strain is Poisson's ratio, and this is a very important property of the material. So concrete will have some Poisson's ratio, steel will have some Poisson's ratio. Those we will see. Then we have one important principle, St. Venant's principle. Now, what this principle says that when loading is applied at a point on a body, it tends to create stress distribution that becomes more uniform at a region removed from the point of application. Okay, stress distribution, how the stress is distributed across the cross section. Okay, so here we have a structural elements, say for example, and we are applying a load here, we are applying a concentrated load here. So the stress distribution will not be uniform here. The stress distribution is uniform away from the point of application of the load. At this point where the load is applied, the stress is more concentrated towards the point where the load is applied. Away from it, the stress is uniform. Okay, so what it means that more stress is here and the stress is average stress is on the sides, which is away from the point of application of the load. So this is how, again once more, we have one element, the width is B, P load is applied here, P load is applied here. So what happens here, we see that near this point, somewhere here, okay, it is very close to the end, B by 4 is the distance here, P is the total width. There, what happens, we see that this is how the stress is distributed. It means that stress is less here, but stress is very high at this point, okay, where the actual concentrated load is acting. The stress is very high in that region. And when we consider sections which are a little bit further away from the point of application, we see that the stress distribution is getting now kind of average. Okay, we see that stress is, there is some stress at the ends, the stress at the middle, this is the stress again at the end. So the difference between the stress in the edges and the difference between the stress in the central portion is now less as we are coming towards the middle, and at the middle it will become average almost. Okay, that is the principle of St. Venant. We may consider, right, what we do when we have a structural limit, we have P force. What we will analyze, we will directly do force by area, right? Pressure by force by area, P by A. The stress, we will say, we will assume that it is uniform, but in reality, it is not the case. That is the principle here. In reality, what will happen? More stress will be here. The value of stress will be more in this region. Then it will be smaller on the edges. Okay. And when we come towards the middle, when we come away from the point of application of the load, the difference between the stress at the edge and at the central portion becomes less and less. So these things are written here. Please see this. Okay, so this will be all for today. If you have any question, if there is something we need to again discuss, let me know.